So with this lesson, we begin learning to predict the products of chemical reactions, or if there's no reaction at all, how to show that with a chemical equation. In this lesson, we're going to be looking at single replacement reactions. So the way that you use this activity series of metals, is to predict whether a chemical reaction will happen if you have a single replacement reaction. So this is only used for single replacement reactions. Okay? So you only use this if you were talking about single replacement reactions. Maybe you want to write that down. Okay? If you can't remember that tomorrow or tonight when you're doing your homework, write it down. The activity series of metals and halogens is only used for single replacement reactions. So I'm going to write out a single replacement reaction and show you how you use it to predict whether a reaction will occur and what you use it for and how it all comes out in the chemical equation. Yeah, the activity series of metals and halogens is only used for predicting whether or not a single replacement reaction will happen. Now, if you'll notice on the activity series that I have here, and some activity series are written a little bit differently, and you have to kind of make more inferences than we're making here, because what I have here is the metal itself when it's not an ion, and I have next to that the column of the metals when they form an ion. And I'm only listing one kind of ion here. There are actually other ions that could form, but we're going to try to keep this somewhat simple by just giving you one ion that could form. It also could be the ion in a formula. Now, the way this works is if the metal or hydrogen in these columns, the metal that's by itself, that's this column right here, is higher vertically than the ion in the formula that's next to it, then the metal will displace the ion. Okay? The metal's higher, it'll displace the ion that's below it. All right? So let's look at this problem here. We've got calcium. So on your activity series, put your finger on calcium. Okay? Make sure you can see where calcium is. All right? And then we want to find the ion. We're trying to find the thing that's like this. This is the part that's by itself. And we want to find something in this formula that's like it. And in terms of the word like here, there's only two categories: metals and halogens. So it's either like a metal or it's like a halogen. Okay? So we're going to look here, we're going to see we have a metal, calcium, and we're going to look for the part of this formula that is like it in the sense that it is also a metal. And so we go down here and we find chromium. Okay? And indeed, this is chromium 2. And the reason you know it's chromium 2 is that nitrate, this polyatomic ion here, has a 1 negative charge. We have 2 of them, so the charge on the chromium has to be 2 plus. Okay? So this is chromium 2. So since calcium is higher on this activity series than the chromium 2, the calcium will displace the chromium. And so we're going to have a reaction here. Sometimes you don't have any reaction. We'll look at that next. But calcium will displace chromium. So here's calcium. And the calcium ion that forms is calcium 2 plus. And so we're going to put it with 2 nitrates. Okay, and then that's going to mean the chromium is by itself. When metals are by themselves, what physical state do they have in normal room temperature and pressure? Almost always a solid. Mercury is the primary example of a liquid metal. And there are no gaseous metals unless you count hydrogen, but that's a whole theory that goes outside the scope of this class. All right, and that's it. All right, you just got to use the activity series to predict whether a reaction will happen or not. Okay, so let's look at another one now, an example of one where no reaction occurs, and look at how you're going to write that when it happens. Let's say I've got nickel, the metal, it's by itself, and I'm going to use aluminum chloride. Okay? Nickel and aluminum chloride. So nickel, and you put your finger right here where nickel is, okay? And then you find the part of the compound that it's like, That's aluminum. This is aluminum with a 3+ charge, and aluminum only has 3+ charges. In this case, the metal that's by itself is lower than the corresponding metal ion in the compound. If it's lower, it's not more active. It won't displace the aluminum. So in this case, no reaction occurs. And you just write NR. Does that make sense? All right, you ready to practice now? Yes. What do you mean 2 in the first one? Instead of, that would be a double replacement reaction. We haven't gotten to that yet. Let's stick with the single replacement reactions right now, okay? So his question was, what if I had a compound over here instead of a metal by itself? That would not be single replacement, okay? Now, remember, halogens also work in a similar way. Let me give you an example of a halogen. So I've got aluminum chloride here. Let's use that again, but use it in the halogen sense, because chlorine is one of the halogens here, okay? So instead of using nickel here, let's put some fluorine gas. And we're going to bubble that through a solution of aluminum chloride. All right, so now we're going to look down here for the halogens, because in this case, I don't have a metal that's by itself. I can't use the metal activity series if I don't have a metal. Okay, I've got to use the halogen activity series because that's what I have is a halogen, because fluorine is here in the halogens column. Okay, so will fluorine displace chlorine? If it's higher on the activity series, it will. And the fluorine F2 gas is higher than chlorine, the ion over here. As a result, then fluorine is going to displace this chlorine. And we're going to get aluminum bonded with the fluorine, and we're going to get chlorine by itself. Now we still have to balance some formulas here. Okay? Let's start with chlorine, because you need to know that fluorine, chlorine, and for that matter, oxygen, nitrogen, and hydrogen are all diatomic gases. We mentioned that before, but this is where it's going to be really important that you know that. It's kind of indicated to you here. If we displace chlorine, the ion, it's going to form chlorine, the diatomic gas. Okay? So chlorine has to be a Cl2. If you write just Cl by itself as a product of a reaction, that's going to be wrong. Now, it might just be Cl if you bond it with something, but by itself, chlorine has to be Cl with a subscript 2. These are all gases. Well, fluorine and chlorine are always gases. Okay? Hydrogen, oxygen, and nitrogen here, always gases under all the conditions we deal with. Okay? Bromine is most of the time going to be a diatomic liquid. Bromine is mostly a diatomic liquid. Iodine's kind of funny in that it's either going to be a solid or a gas at room temperature and pressure. So it goes straight from being a solid to straight being a gas. If I had a little solid chunk of iodine in my hand, it would be a deep purple, almost black-looking chunk, but it would start to become a gas. Okay, just like carbon dioxide doesn't go through liquid; it becomes a gas, and you'd have a purple gas coming off out of my hand. Now I wouldn't do that because it's not really a good idea to hold pure iodine in your hand, but you could do that. Okay, and so you need to know this is always a gas and it's diatomic. This is always a gas and it's diatomic. Nitrogen and oxygen are always a gas and diatomic. Hydrogen, when they're by themselves, are always diatomic gases. Okay, bromine is a liquid. Iodine could be a solid or a gas, and so you need a little more information to figure that out. Okay, all right. So back to this. Now this we'll find out later on. We'll figure out later on how we're going to figure out when this is going to be aqueous or something else. Let's just say for right now that it's going to be aqueous because we have it in liquid. Okay, we'll get to the when you figure out something's going to be dissolved in water and when it isn't later. We have to balance this. So what charge does aluminum have? What charge does aluminum always have? 3+. What charge is fluorine going to have? And what does it always have? What is its charge all the time? -1. Now it says so right here too. That's a help. So how many aluminums and fluorines do I need to have a balanced compound? Well, there's no charge overall. 3 what? 3 aluminums or 3 fluorines? 3 fluorines. Okay? Aluminum has a 3 plus charge, fluorine has a 1 negative charge. You balance it with 3 fluorines and 1 aluminum. Okay? And so that's the reaction. Now I need to show this as a gas, and we talked about that. Okay? We've given you enough information for you to figure out whether it's a gas or a liquid. And iodine is sometimes kind of tricky, so we won't worry about that too much right now. Okay? All right, now you ready for some practice? Well, whether you're ready or not, here we come. Write these down and solve these problems. You may work with a learning partner. Let's go back and look at this for a minute, because this one ended up being balanced. This one's not. Let's balance this one right quick. FAlCl. 2 fluorines, 1 aluminum, 3 chlorines, 3 fluorines, 1 aluminum, 2 chlorines. Okay, so to get the fluorines balanced, I need a coefficient 3 in front of this fluorine and a coefficient 2 in front of the aluminum fluoride. Does everybody understand why I did that? It's important that you understand, because you've got to be able to do this. I'm not hearing any objections. I assume you know what's going on. So this is going to give us now 6 fluorines, 2 aluminums, and 6 fluorines over here. Now that I have 2 aluminums on both sides, on this side, I need 2 on this side. Put a 2 here. That's going to give me, excuse me, 2 aluminums and 6 chlorines. And now I need a 3 here to get to 6 chlorines. Okay? Can't leave the equation unbalanced. Got that? All right. AQ means aqueous, means dissolved in water. Okay. S means solid. G means gas. And of course I don't have an L on here, but L would be a liquid. Okay. The difference between a liquid and aqueous is that aqueous means you've dissolved something in water, while water itself is a liquid in most of the time, not all the time. If we were using water, a liquid, we write L for its physical state. Okay, so solve these 3 problems. You already know it's single replacement, so we're not going to classify it, but you want to find out. We're going to have a reaction. If there's no reaction, you write NR. If there is a reaction, you're going to write the products, balance the formulas, and then balance the equation. Got that? So you have to balance the formulas before you balance the equation. You can't do one before the other. You can't balance the equation before you balance the formulas. Got to balance the formulas first. All right, let's look at this problem. We have magnesium, which is a metal. Magnesium is located here. It's on the left-hand side of the stair step, so it's a metal. We have zinc in the formula. It's a metal. It's right here. It's on the left-hand side of the stair step. So if a reaction is going to occur, this metal that's by itself has to displace this metal in the compound. Okay? And so to know if it's going to occur, we're going to use the activity series here. So we're going to find the metal that's by itself. That's the magnesium. There it is. Then we're going to find the metal ion in the compound. And the zinc is right here. So magnesium, the metal that's by itself, is higher than the metal ion in the compound. It's an ion. Whenever a metal bonds with a nonmetal, it forms an ion. It always forms a charged particle. And so since the metal that's by itself is higher on the activity series than the metal in the compound, then this is more active. It will displace the zinc. We do have a reaction. So magnesium then is going to join up with the back part. Magnesium can't join up with zinc. Metals aren't going to join up with zinc in these kinds of equations. Yes? Oh, I'm sorry. Magnesium is not going to join up with zinc because they're the same thing. They don't want to be together, okay? Magnesium is going to join up with the chlorine, all right? It may not be politically correct to say so, but it's kind of like, you know, guys usually go to the prom with girls. Okay, this is like guys and girls here. Okay, so magnesium is going to join up with the chlorine. And we haven't balanced that yet. I just put them together. I haven't balanced them. Okay, I don't carry this 2 over. Now let me tell you something about subscripts. Subscripts don't travel unless they're part of a polyatomic ion. Might want to write that down. Subscripts don't travel unless they're part of a polyatomic ion. Okay? Polyatomic ion subscripts usually travel. That is to say, they go from one side of the arrow or equation to the other. All right, then. Since I've kicked out the zinc, it's by itself. All right? Now, zinc is a metal. Most metals are going to be what physical state? Solid. So we know what that's going to be. Now, you don't have enough information yet to know what physical state this is, so I wouldn't hold you to that, but we'll get to that. But this is going to be aqueous. And magnesium's 2 plus and chlorine's 2 negative, so there's the formula. Okay? Then if we're going to do the atom inventory and balance the equation, I'm going to write these out. And we can see that it's already balanced. Okay? All right, then number 2. We've got cobalt, a solid, plus copper. This is copper 2 chlorate, which is aqueous. Okay? We need to know if cobalt will displace copper. Now look on the activity series, and we see that cobalt's right here. Okay? Let me raise this up so you can see all of it together maybe. Cobalt and copper. Here's cobalt, and copper's down here. Cobalt's the metal by itself. Copper's the metal in the compound. So will cobalt displace copper? Yeah. If the metal by itself is higher, it'll displace the metal that's in the compound, the metal ion in the compound. So now cobalt is going to join up with chlorate. Cobalt's going to form a 2 plus charge. Okay. Chlorate has a 1 negative charge. So I need 2 chlorates. And then you wouldn't know this, but this is also aqueous. And that means that copper is going to be by itself. It's a metal, so it's going to be a solid. Okay? Balance the compound, balance the formula rather, balance the equation rather.
Why would you have CL3? Why would you have it?
Polyatomic ions stay together. Okay? They tend to stay together. They don't always do that, but most of the time in this class they will always stay together. So I got 1 cobalt, 1 copper, 2 chlorine, 6 oxygens, 1 cobalt, 1 copper, 2 chlorines, and 6 oxygens. That one's balanced. Okay?
Is it always supposed to be balanced? Is that how you use
Nope. It isn't always supposed to be balanced. That's why we're checking it, to make sure. Okay? And the last problem was this one. CrBr2, which I listed as being aqueous, and then chlorine, a gas. Okay? So now we're looking and seeing that the thing that's by itself is not a metal. Chlorine is over here in the halogens column. So we're not going to use this part of the activity series. We're going to use this one down here. Okay? So chlorine, which is right here, is higher on the activity series than the bromine in the compound is. Okay? So bromine ions here are lower than the chlorine. So this chlorine will displace the bromine. So now we're going to put this Cr with the Cl, and we're going to have the Br by itself. Okay? So bromine, we said a moment ago, or earlier, it's going to be a liquid. It's still diatomic, but it's a liquid. Okay? Now you wouldn't know this, but this is aqueous. We need to balance it, and it says that chromium here, where's chromium? There it is. Chromium, we're going to write as being having a 2 plus ion, 2 plus charge, okay? So this is chromium 2 bromide. It'll be chromium 2 chloride. Chlorine, when it's in a binary compound, has a negative charge, okay? So I need 2 chlorines for every chromium. And so now we're going to balance everything. 1 chromium, 2 bromines, 2 chlorines, 1 chromium, 2 bromines, 2 chlorines, okay? So all these equations turned out to be balanced, all right? Not all of them are going to be balanced, but in this case they turned out to be so. All right, any questions about that? If it's not balanced, it might mean you just have to balance it. So we learned how to balance equations yesterday. That was your homework also. So if we get to this point and they're not balanced, then you need to balance them. That make sense? All right then. Yes, what's your question?
You said subscripts don't travel if they're part of the what?
Subscripts don't travel unless they're part of a polyatomic ion. So if you look at your list of common ions, okay, this list here that I give you in your test references, if I have a bromite ion as part of a formula on the left-hand side, then I'm going to move that bromite intact to the other side of the equation. Okay? That's what that means. All right, then. So let me show you something about this homework problem real quickly. Okay? I'm going to give you a clue. Zinc, let's see if I can put it up here where you can see all of it at one time. Zinc is higher than hydrogen. But notice here, the hydrogen ion is 1+, but hydrogen, the gas, or the thing that's by itself, is H sub 2. We said earlier that hydrogen, oxygen, nitrogen, chlorine, fluorine, all those are diatomic gases. So if zinc displaces hydrogen, it doesn't make just H, it has to make H2, and it's a gas. Okay? Just to give you a heads up on that one.